Hello guys, welcome back to another video. Today I'll show you how to find the square root of x without using a calculator. In fact, we are going to use calculus because in calculus we have a lot of tools to approximate things like derivatives and integrals. So we are going to do that using calculus. So let's try to find what the square root of 10 is. Why do we need calculus in the first place? Well, because we know that we could define a function f of x to be equal to the square root of x, right? And what is the square root of 10? Well, it's just f of 10, because f of 10 is the square root of 10. Nothing new right now, right? We just have to find what f of 10 is, because it is the square root of 10. So, why do we need this function? Well, look at this picture right here. We have our yellow function, that is the function f of x equals the square root of x, the function we're interested in, and we have another function r of x, that is a linear function. It is a line on our xy plane. Well, we're interested in the value of the square root of 10, and we need somehow a way to approximate it. And there is a beautiful way in calculus to do it, and it's called linear approximations, and we need derivatives to do that, but nothing too crazy, but it is absolutely incredible. So how can we do it? Well, as you can see, if we sit at this point, this generic point, then we're going to be specific for x equals 10, but for now let's call this point x naught. Well, at x naught, notice that r of x can approximate f of x if it has the same slope of f of x. And I'll explain you how this works in a moment. First of all, r of x is just a linear function, so we all know that it is described by the equation mx plus q, where m is the angular coefficient. It's basically its first derivative, that it is a constant, and describes how steep is the slope of the function. So r prime of x equals m, and q is just the point where this function intersects the y-axis. Basically, we have to find our equation, a function of the form mx plus q, to approximate our function, that is the square root of x. Notice that the two functions at the point x naught have the same slope, and this is very important for our approximations. And since they have the same slope, it means that a prime of x, because a prime of x is constant while f prime of x is not constant, because as you can see, the slope of the function, this f of x equals the square root of x, changes, so it's not constant, but it is equal to a prime of x at the point x naught. The two slopes are equal, and we know that r of x equals m, that is f prime of x naught times x plus q, but we still don't know what q is equal to. Well, there's another thing that the two functions have in common, that is, they go through this point at x0. In other words, at x0, f of x naught equals r of x naught. They go through the same point in the xy plane. So, if x naught equals r of x naught equals f of x naught, we know that this equals to mx plus q, and mx plus q at x0 is just f prime of x0, that is m, times x naught plus q. And now we have this nice equation, f of x naught equals to f prime of x naught times x naught plus q. And we can simplify q, just take this to the other side of the equation, so we have that q equals to f of x naught minus f prime of x naught times x naught. Now let's substitute q in our previous equation. So we have that r of x equals to f prime of x naught times x plus q, and we found that q is f of x naught minus f prime of x naught times x naught. And we can even factor out f prime of x naught, so we have that this equals to f prime of x naught that multiplies x minus x naught plus f of x naught. And this is our linear approximation of f of x at the point x naught. But how is this useful? Well, let me explain you how this works. Okay, so before going to the next step, we have to find what f prime of x naught is equal to. Well, this is so simple. Since f of x equals the square root of x, we can find the derivative of f of x, so f prime of x equals, using the power rule, we get that this is 1 over 2 times the square root of x. And this is something so trivial to do, but this is f prime of x, so f prime of x naught, just substitute x naught in this equation, we have 1 over 2 times the square root of x naught. In other words, r of x equals to f prime of x naught, so x minus x naught divided by 2 times the square root of x naught plus f of x naught. So if we have this equation and we place our function at a point x naught that we know what the square root is, that is close to 10, we can find what f of 10 is. I'll explain you how this works using this graph. If this is the point 10 and this is f of 10, basically the white line, we can place our function at a point x equals 9 because we know what f of 9 is. We know that the square root of 9 equals 3. So if we want to find f of 10, this is approximately r of 10, but with x0 equal to 9. So let's try to do it. Let's try to find r of 10 using x naught equal to 9. So this is x, so 10 minus x naught, so 9, over 2 times the square root of 9 plus f of x naught, that is plus the square root of 9. And we can simply do it. This is not that difficult. Let me clear a little bit the board. And this equals to 10 minus 9 is 1 over 2 times the square root of 9. The square root of 9 is 3, so 2 times 3 is 6, plus the square root of 9, that is 3. And we can sum this, and this is 6, so 1 plus 18, so this equals to 19 over 6. And we now know that the square root of 10 is approximately 19 over 6. And you may say, well, how close are those two numbers? Well, now you need your calculator. You can even approximate this without a calculator, but I'm going to use a calculator to give you the exact result. So we have that this number is 3.16666, and it goes on forever like this, while the exact value of the square root of 10, or at least an approximation to the square root of 10, is 3.16227, etc. So this is a fairly good approximation, I have to say. Those numbers are very close, and we did it in a super cool ways. So how cool is that? We use a number close to 10 that we know what the square root is, and then we approximated our function using a fantastic linear approximation, and we could have done even better than this using Taylor's series, and that is so cool. It involves higher derivatives of those functions, but that could get even more complicated, so we need in those cases a real calculator. But this is how cool. I mean, just a linear approximation gives us this amazing result that they're so close, two decimal places. So how cool is that? Let me know in the comments if you would like to see other videos like this, and don't forget to subscribe to my channel, share this video with your friends, and as always, until next time, bye.